Today we'll be building a spreadsheet simulation model of genetic drift. My colleague Jed mentioned that evolution is often described as a change in allele frequency from one generation to the next. And if you think back on your Hardy-Weinberg exercise, you'll remember that Hardy-Weinberg predicts that allele frequencies will remain constant from one generation to the next, unless there is some kind of evolutionary force at work. What kind of forces could there be? Well, Jed mentioned a few: mutation, natural selection, gene flow, non-random mating, and the last one is this process called genetic drift. And genetic drift is one of those concepts that's pretty tough to describe, and our hope here is that by doing a simulation model, we'll really build some intuition about what drift is all about. In our spreadsheet, we've set it up so that you can enter a parental population size in cell B5 and then let those parents reproduce offspring. And you can enter the number of offspring that are produced in cell C5. The individuals are labeled down column A, and we've numbered them from 1 all the way through 500. So the spreadsheet itself can be pretty flexible, meaning that we can deal with any size population as long as we don't exceed 500. Let's assume that we're dealing with a population of 10 parents, and they will produce 10 offspring. So the first thing we need to do is down column B, assign a number 1 if the individual is actually part of the parental population. Otherwise, we'll assign a 0. We'll do that with an if function, and we'll simply say, is the number associated with the individual less than or equal to the value stored in cell B5? And if it's true, then we'll have the spreadsheet return the number 1, otherwise we'll have the spreadsheet return a 0. And if we copy that through, now we can see that the first 10 individuals now make up our parental population, and everybody else has a 0. And later you'll see that the zeros will not enter into our calculations at all. The next step is to assign a genotype to each and every individual in the population based on the frequencies you enter for the A1 allele and the A2 allele. If you enter 0.4 into cell D5, that means that there's a number of alleles in the population, and 40% of those are of type A1. And if we enter 1 minus cell D5, it means that the frequency of the A2 allele is 0.6. So by now you ought to know that the sum of the allele frequencies must equal 1. And for this example, we're dealing with just one gene, called the A gene, and this particular gene has 2 kinds of alleles, called A1 and A2, and the population has a frequency of A1 of 40% and a frequency of A2 of 60%. Now, just like we did in the Hardy-Weinberg exercise, we're going to use a random number and use these frequencies here and assign a genotype to each individual. And I'm going to enter it in cell B6 because we're going to store this as a permanent formula. We basically took an if function and we asked Excel to first determine if a random number was less than or equal to the frequency of the A1 allele. And if it's true, then the individual would receive an A1 allele, otherwise it would have an A2 allele. So by using the random number, any random number between 0 and 0.4 is going to result in an A1, otherwise it will result in an A2. And in this way, our simulation will reflect these numbers that are stored as entries. If we press OK, we're halfway there to assigning a genotype, because we know that individuals carry 2 alleles for every locus if they're diploid. So we simply need to copy our equation and then join it with the same equation, and that generates our genotype. At this point, we can use that same formula and assign genotypes to all of our individuals in the population. So we'll copy that formula, and then we'll select cell C9 and we'll paste the formula in, and then copy it through. So now we have our parental population identified. At this point, we can summarize our population by counting the number of A1A1 homozygotes, the number of heterozygotes, and the number of A2A2 homozygotes. And once we have these numbers, then we can calculate the allele frequencies for this parental population. So our parental population is going to be stored in this row, row 4, that's called time step T. Now to enter this formula, we're going to use a different kind of function in Excel that you may not have used before. It's going to be called an array formula. And we'll enter it just like we do other formulas, but we'll type it directly into the formula bar. And I'm going to try to walk you through this fairly slowly so that you have a good feeling for what's going on. The first thing we're going to do is start an equation, and we're going to select all of the individuals down column C. Those are our genotypes, and we're going to ask, are these values equal to the genotype stored in cell I3? And we close the parenthesis. Now that in and of itself is not an equation. What's happening here is that Excel is looking at each and every entry in this array, and it's comparing it to the value stored in I3, and it's asking, are they equal? And in the background, Excel is storing an array of the same size and is returning true or false. So this would look like an array that has the following: false, 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 true, false, true. And the falses can be interpreted as a 0, and the trues can be interpreted as the number 1. And because of that, we can now multiply that array by the count array. So we'll enter a multiplication symbol, and then we'll select the count array. We'll close the parenthesis, and let me tell you what this is doing now. It's taking the true-false array and multiplying it by the count array. So here we have 1 times 0 is 0. This array is 1 times 0 is 0. 1 times 0 is 0. 1 times 1 is 1. So as a result, in order for us to score a 1, the individual needs to be part of the parental population, and it also needs to have an A1A1 genotype. Now we're not done yet, because right now we're just storing 2 arrays. So now we need to tell Excel what to do with the values in those arrays, and we want to sum them. So right after the equal sign, we'll enter the word sum, and we'll open the parenthesis, and then we'll close the parenthesis on the far right side. Now don't press OK, because this is an array formula, and it means that you need to enter Control, Shift, and then Enter if you're using a PC, and you'll see then that Excel generates the result. So my result is that there are 3 A1A1s in the first 10 individuals. There's 1, there's 2, and there's the third. you'll see that the array formula has these curly braces added to it, and that alerts you to the fact that it's an array formula and it must be entered with those unique keystrokes. Now at this point, we should be able to copy this equation through and then click on an entry and just make sure that the references are the same. So here we're counting the A2 homozygotes and it looks to be correct. We'll press Control Shift and Enter. And you might remember that the heterozygotes are going to be a little more problematic because we need to count not only the A1, A2 heterozygotes, but also the A2, A1 heterozygotes. And the fastest way to do that is to erase this formula and simply calculate it as the parental population minus the A1 homozygotes minus the A2 homozygotes. And that gives us our results. Now it's really important that you spend some time and just double check to make sure that these are actually correct and they're returning exactly what you're seeing for your first 10 individuals. Okay, what's next? Well, the next thing is to calculate the allele frequencies. And at this point, this should be no trouble for you. The frequency of the A1 allele is going to be equal to 2 times the number of A1 homozygotes, because each of those individuals carries 2 copies of the A1 allele. And we're going to add to that the number of heterozygotes, because each heterozygote carries a copy of the A1 allele as well. And then we'll divide by 2 times the population size. Why 2? Well, each of these individuals carries 2 alleles for that particular locus. So there are 20 alleles across the population, not just 10. For the A2 allele frequency, it's going to be 2 times the number of A2 homozygotes plus the number of heterozygotes divided by 2 times the population size. And so now we're dealing with our parental population. We've simulated them. We've simulated 10 individuals. And we end up with 2 homozygote A1, 4 homozygote A2, and 4 heterozygotes. And our resulting allele frequencies is 0.4 and 0.6. Now remember, these values here are used to simulate the population, but the results actually are storing the actual allele frequencies from that simulated population.